On the board right now, you see two types of, not lenses, but mirrors. A converging mirror, which in this situation produces an image of a guy's face that is massive but upright, but in other situations will produce an image that's completely different. That's called a converging mirror versus a diverging mirror, which is the kind of mirror that you sometimes see in a parkade, or if you go swimming at the pool in Okotoks, you see at the corner of the hot tub. You used to see them in stores, convenience stores. Now it's just video cameras, but you used to see them in stores so the store clerk could tell if somebody was shoplifting or not. You see them in cars, actually. See them in cars sometimes in the corner of one of your side mirrors. Okay, convex, slightly convex mirrors. And it allows us to see, in this case, you can see a wider range. Now, it does have the effect of making the image smaller, but at least we can see more of it, right? Which is helpful if you're trying to pass somebody in your car, or if you're a lifeguard at the pool in Okotoks trying to see more area, right, at once. Now, notice that a converging mirror is also known as a concave mirror. So converging mirror is thinner in the middle than it is at the edges. That's opposite to lenses. A converging lens was a convex lens. Converging lens, convex, converging mirror, concave. Diverging lens was concave. Diverging mirror is convex, thicker in the middle than it is at the edges. Now, this converging mirror means that rays that are parallel to the principal axis will converge at a focal point. The diverging mirror means rays that are parallel to the principal axis will diverge away from a focal point. Just like with lenses, they diverge away, except with lenses, they didn't reflect, they refracted and diverged away. If you look at the front side of the template that I gave you, you're going to see this picture here. What kind of mirror is this? Concave or converging? Concave, converging. We're going to put an object out here, way out here, somewhere beyond the focal point, and in fact, somewhere beyond 2F. One more thing that I want to mention to you here. If this mirror is circular, and we completed the circle, 2F would be right smack in the middle of that circle. So sometimes you don't see it labeled 2F here. Sometimes you see it labeled R. It means the same thing. For a mirror, R, the radius, right, the radius of the circle of the mirror, is twice the focal length. So sometimes you'll see it written either way. Now, we're going to draw two rays here. There's three that we can actually draw. There's a million that we can actually draw, but three that we're going to have to draw throughout this exercise, but there's only two that we have to draw for this particular diagram. I'll show you the third one for the diagram, but you'll see why in a minute it's not necessary. Yeah. Yes, right up there. Take one of these if you need a ruler and hand it on to the next person. Just make sure you turn them in at the end of class, okay? I'll start it right here, and if you guys need to grab one, just grab one from as it goes back. All right, so first ray. Top of the object parallel to the principal axis, and it's going to reflect down through the focal point. Now the second ray is not going to go down through the optical center because we don't have an optical center of a mirror. The second ray is going to go down through the focal point. Where do you think it's going to go? Take a guess. An educated guess here. It does not reflect to the focal point. Rather, if the ray that goes parallel goes through the focal point, the ray that goes through the focal point is going to go parallel. So this image ends up being formed right here. It is smaller. It is inverted. And it is real or virtual. It's real, solid lines intersect. I want you to think back to the ray diagram for lenses, for converging lenses, when we had the object placed beyond 2F. The characteristics we got were smaller, inverted, and real. Once again, real is upside down. It's the exact same characteristic as we got for this mirror, sorry, for this lens, the converging lens. Now, let me show you the third ray. Okay, we don't need to draw that here, but let's just show it to you anyways. The third ray goes from the top of the object down through the center, or the 2F. Hits the mirror, and where is it going to reflect? Right back upon itself. Where does it intersect? Same place the others ones intersect, right? So we get an image that's still in the same place if we had chosen to draw that third diagram. I'm going to erase that because it's not necessary to determine the characteristics of this image. It just kind of clutters up the diagram. Second diagram, we're going to place our object at 2F. First ray is going to go parallel down through the focal point. Second ray is going to go down through the focal point, and it should reflect back parallel to the principal axis. Now, those should intersect directly below our object, and it should be exactly the same size. It should be inverted, and it should be real. Just like it was for a converging lens when the object is placed at 2F, we get an image that's same size, inverted, and real. Starting to see another pattern. The pattern that we're seeing now is that the ray diagrams for mirrors, although the ray diagrams look different, the characteristics end up being exactly the same. Next diagram. We've got our object placed in here. Now for lenses, you might remember that we got an image that was real, it was inverted and larger. Let's see what happens here. Ray down through the focal point, down through the focal point, parallel. Oh, look at that. Go figure. We get an image that is real, inverted, and larger, just like we did with a converging lens where the object is placed in between F and 2F. Next one, our object is at F. Right, if this is F, this is 2F. First, or 2F or R. Say the first ray is parallel down through the focal point. This one's a bit tricky. The second ray we can't draw because it goes down through the focal point while we're at the focal point. So the second ray is the one that's going to go through the center or the radius of curvature, 2F. So we're going to draw this one up away from the object. It strikes the mirror. Pretend the mirror goes all the way around there. Strikes the mirror. And then it reflects back upon itself through that 2F. They don't intersect. That means that we have no image formed, which is exactly what we should expect, because that's exactly what we saw when we had a converging lens when the object was placed at the focal length. So if you're standing in front of this mirror, way back, you're going to see yourself in this mirror upside down and smaller. And then as you approach the mirror, you're going to see yourself upside down and same size. And then as you get closer still, you're going to see yourself upside down and bigger. And as you get closer still, what's going to happen? You're going to look in the mirror and you're not going to be there because there's no image formed. And the last one for this type of mirror, when we place our object inside the focal length, parallel down through the focal point, this one goes up away from the focal point, reflects off of the mirror, back upon itself through 2F. We extend those rays, and lo and behold, just like with a converging lens where we were inside the focal point, the image formed is going to be larger. It's inverted, sorry, it's upright, I should say. and it is virtual. Virtual because dotted lines intersect, meaning we couldn't project it onto a screen even if we wanted to. On the back side of your page, you see what kind of mirror? Convex or diverging. Remember when we had a diverging lens? All 5 of the ray diagrams are the same, right? With a diverging lens, it didn't matter where we put our object. The image formed was right side up, virtual, and smaller. We're going to get the same thing here. Okay, the patterns still hold. The exact same patterns hold with mirrors as they do for lenses here. Let's put our object way out here. First ray is parallel to the principal axis. It's going to diverge away from that focal point. So if we extend it back, it's going to look something like this. Whoops. Let's try this. Extend it back, it's going to look something like this. And then that second ray, just drop your pens for a second and watch me on this second ray. Because this one, people get messed up on this one. The second ray goes toward the focal point, but it can't make it all the way. How come? There's a mirror in the way. There's a mirror in the way. So it's going towards the focal point, but then it reflects off of the mirror like this, parallel to the principal axis. So parallel up away from the focal point, then it goes toward the focal point, and then parallel. Let's extend that reflected ray. And we find that the image formed is, what do we expect to see? Smaller, upright, and virtual. Dotted lines intersect means that we could not project it onto a screen even if we wanted to.